Okay, we're going to be talking about this concept of concavity and how we can use it for curve sketching. So the important thing to note is that if a function is said to be concave up, that means that its first derivative is increasing. So there's a connection. So what I want you to see here is that as the function is concave up, I want you to note what's going on here with the tangents that are being drawn. Okay, so as the tangents are being drawn, look at what's going on with the steepness of these tangents. Okay, so there's something to note there. All right, so whenever the function is concave up, all right, and here's this where it says second derivative test down here, the second derivative is positive. Okay, so what does that mean? The second derivative, f double prime, is positive. All right, now whenever it's concave down, so I'll erase that and I'll show you that part. Here's where it's concave down. All right, whenever it's concave down, I want you to make note of the steepness of the line, the tangents, if you will. Look at what's going on there. There, the first derivative is decreasing. Okay, but long story short, if we look at the bottom part here, if the second derivative is negative, then it is concave down. All right, so let me highlight this concave up here, and I'll make that important little note that the second derivative will be negative. All right, so that's what we're looking for. If we're talking about concavity, we can sketch a graph roughly. We can figure out what it would look like conceptually without even looking at a calculator, because we look at different parts of the derivative. Okay, so we're going to take a look at a couple of problems. We're going to talk about where the intervals of concavity are, whether it's concave up or concave down, but really simple examples. So let's take a look. Okay, so here are a couple of examples. Now, in order to answer the questions, we've got to take the derivative. So we've got to actually find the second derivative. So let's find first q prime of x, and that's going to be 27x squared plus 2. And then q double prime of x, well, that's not too bad. It's 54x. And we set that equal to 0, and we actually get x equals 0. So it's really nice. What all we have to do is draw our wiggle graph here. Looks something like this, and of course negative infinity to infinity, and then we put our potential inflection point of 0. So what we do is we pick numbers before and after 0, and we determine the sign, whether it's positive or negative. So you plug in numbers in here for x, and suppose you pick a -1, well, that's going to give you a -54, so negative, and say you pick +1 right after 0, and you get +54. So this indeed is an inflection point. That's important to note. But remember what we said in the definition earlier was that if the second derivative is negative, it's concave down, and if the second derivative is positive, it's concave up. So I use these little symbols here to determine my intervals of concavity. All right, so I will write that it's concave up, and I denote it CC with an arrow up, and that's going to be on the interval here from 0 to infinity. So I write in parenthesis 0 to infinity, an open interval. And then where is it concave down? Well, similarly, it's from negative infinity to 0. So I will write that as well. All right, so that's where it's concave down. And that right there answers my question. Okay, so let's go ahead and take a look at this next problem here. Move it up just a little bit there. All right, keep that in view so we can see it. And let's find the derivatives. F prime here is going to be 6x squared plus 24x plus 18. and f double prime, not too bad here, 12x plus 24, okay? And then we set this equal to 0. We say 12x equal negative 24, and then x ends up being negative 2. So then all we have to do is check the wiggle graph here, f double prime for negative 2, and again from negative infinity to infinity. And we're going to check, do we have, because it could be that you don't have in an inflection point, and then so the concavity would stay the same. But anyway, we're going to plug in numbers before negative 2 right in here for x, and then after negative 2. Before negative 2 may be negative 3. 12 times negative 3 is negative 36 plus 24 is negative 12, which is, again, we don't care, a negative number. Then you pick something after negative 2, like 0 works. 12 times 0 is 0 plus 24, that's positive 24 again. So here is concave down and here is concave up. And our intervals of concavity we write down here. So where is it concave up? From negative 2 to positive infinity. And where is it concave down? From negative infinity to negative 2. And those are our intervals of concavity. All right, not much to it. I mean, two really, really simple examples. Of course, you can get into more difficult problems if you're asked maybe to use the quotient rule, the product rule, the chain rule. These are really basic, but as long as you know how to take the derivative, you'd work it out the same way. So no matter the level of difficulty of the problem, just keep in mind the wiggle graph comes into play and you're kind of doing this same kind of stuff. Okay, so don't get scared. If the derivative looks overtly complicated, just do it. It's not that bad, and this concept's really easy. And then again, why are we doing this? Because it helps us sketch the graph. All right. When the mathematicians that came up with this calculus stuff were working on this kind of thing, they didn't have access to a graphing calculator like you do now. And you may be wondering, well, we have one now. Why do we need to do it? Because you understand the concept. And there's more applications of this when you're getting into various rates of change in business, economics, and different things like that. And it has a point, and it helps you to interpret what in the world is going on. Okay, so I'll get off my soapbox now. I hope this video was helpful. And as always, like and subscribe.